Jack in the late 70s. I had been here about 4 or 5 years, and one day Britt Chance called me to his office, and he said, "Stan, I have someone here I think you should meet," and it was someone from General Electric. I don't know if you remember that, but he said, "Do you know anything about NMR and how NMR can be of use in imaging?" I said, "No." I had received some papers about the technique. I had seen some test tubes that Paul Latimer had made images of test tubes. But you know, the CT had been introduced in the 70s, and I just couldn't imagine how this technique was ever going to compete with that. But you know, if Britt said it was important, and if General Electric was going to be putting in resources in this, I think I better listen carefully. And I said, "Well, I know very little about it." I said, "You know, Britt, but how can our department learn more about this technique?" He said, "Well, there's a fellow named Jack Leigh who knows everything about everything. And I'll bet you he would be interested in educating the department on this technique." So I went to see Jack, and Jack, of course, at that time was in biochemistry, biophysics. Introduced myself, and I told him, you know, Britt sent me. And his chore was to educate imaging radiologists in this new technique of NMR. It had not yet changed its name to MRI. He said he'd be glad to do it. There was one minor problem. We solved that. All of you who know Jack knew that it was not unusual for him to put in, you know, 10 to 12-hour days working in the laboratory. The problem was his days would not infrequently start at 1 o'clock in the afternoon. Our department, being a clinical department, we had all our schedules and we had all our clinical talks and educational grand rounds and whatever much earlier. So I said, "Well, do you think it would be possible for you to come in to start these tutorials at 11 o'clock in the morning?" And he said, "Well, I don't know about that. I'll have to speak to Judy about that." And I don't know if Judy actually drove him in those mornings or not, but we got him here at 11 o'clock in the morning, and he used to fill up blackboards with first with electromagnetic spectrum, educate us on what a T1 versus a T2 was. And I don't know how well we learned, but we certainly embarked on this adventure in a new area of imaging. But Jack was much more than just someone around to teach us about MR. He was a very unusual person, as all of you know. And, well, I can tell you, there are many, many funny stories about Jack, obviously. When he wanted to put in his magnet, I was concerned because, you know, to put in a 1.5 Tesla magnet in an environment that was not protected could be a problem. He said, "No problem at all." I said, "Well, how are you going to do that?" He said, "Well, there's a swimming pool." I said, "What swimming pool?" Well, I don't know if many of you know the story, but Blockley, the building that the center is in, was originally the nurses' residence for the Philadelphia General Hospital. So when Philadelphia General Hospital was operational, Blockley was their nursing home, and in the basement of the nursing home, was nursing residence rather, the nursing residence had a swimming pool. And how, you know, Jack or Britt found that or even thought about it, but certainly they were able to put it in. There was no significant shielding and never presented a problem. I guess until about a decade later, after Jack moved to our department, when Bill Kelly was our dean, and Bill wanted to put up a research building immediately adjacent to the old Blockley. Now, putting up this new building, he was going to significantly affect Jack's laboratory because he'd go right through it. And Jack was furious, and he said, "Who's going to do this?" I said, "Well, you know, Bill Kelly wants to do this. I'll go see him." So he went to see Bill, and he said, "Bill, I'd like to see the plans for that new building." And he said, "Well, you know, it's a document, you know, several feet high." He said, just give me the plans for that building." And he took the plans, went home, and after about a week, he came back and he said, "The building's designed all wrong." He said, The entrance to that building should not be where it's placed. The entrance and that building should be off Curie Boulevard, and it's a much better place for it, and if you do that, it won't affect our laboratory. Well, they had already they haven't really bid it out yet, but the plans were really complete. And he met with the architect, and I couldn't believe it, but the architect came back to me and said, you know, Jack's right. That's a much better place for the entrance, because if they further develop the Philadelphia General Hospital and put a more research building, it'll be a logical place to have people come and go. So, in effect, he redesigned the entire entrance and the building, which was this new research building. Well, I guess it was 1990 that Jack moved, or 1991 that Jack moved from biochemistry, biophysics into radiology. And the reason was that all his trainees would go into imaging. He had much more in common with the imaging scientists we were beginning to put into our facility. Franz Machinsky, who was then chair of biochemistry, biophysics, had no objection to this, and he agreed that Jack's interests were more aligned with what we were doing. So Jack moved into radiology. I had done a lot of recruiting over the years, and many new faculty asked for different kinds of things. I never had anyone quite like Jack. It was just the opposite of what you would normally anticipate. When you normally recruit somebody, they want to see their office, they want to see their furniture, they want to see where the secretary is going to be sitting. Jack didn't want any of this. As a matter of fact, he viewed that as an impediment for science. He felt if anyone is going to be spending money, the money should be going into science and not in furniture and carpeting and all the rest of it. And for many of you who may remember how you got started in Jack's facility, he would ask you to go to a dumpster, find a desk and a chair, and move it into his laboratory, and that was your new space. Well, I could not convince Jack to buy new furniture or have us buy furniture for him. And Susan may remember those days where the only way we were able to convince him to take the furniture that's presently there is to convince him that it was secondhand furniture. And we bought it at not quite an auction, but eBay didn't exist. But if eBay had been there, I would have probably said we got it on eBay. The very large conference table that all of you know down in his center was a conference table that used to be in the Silverstein room. And when I first showed it to him, he said, "Oh, I can't. It looks like an insurance company if I have something like that in my." He had a terrible fear of having his facility look corporate, and it further moving into a clinical department in the school. He didn't want to be viewed as an IBM or an insurance. But I explained to him that if you in fact do not take this table, then you throw it out. He said, "Well, I don't want to throw it out." So, and I think he had actually loved it over the years. I mean, this to me is the vision and the view I have of Jack. Sitting in his open desk, people surrounding him, papers surrounding him, and I think I commented to somebody here this morning that perhaps his greatest talent was to be able to ask questions. He always asked questions, and then he would leave. And the questions he would ask would be very disruptive questions very often. And the only one that had an office with walls around it was Susan, because he said, well, she does business kind of stuff, and she has to be protected. But this is where Jack did all his work. It was a remarkable facility, and none that I had ever seen anywhere else. Jack would sit there as the leader of this group, but he would be irreverent to everybody, regardless of your title, whether you were a Paul Latimer with a Nobel laureate, or a chair, or of a department, or a fellow. I think he was the one person I've known over the years that treated everybody about the same. We'll mention for a moment, there were only two people he really viewed differently and treated differently, and that was his professional parents. That was Rich Hansen and Mildred Cohn, and you'll hear from them in a moment. When I went through the number of trainees he had, I don't know, it could be over 100, but I just kind of said, well, how many people did he train that ultimately stayed at Penn and had a faculty appointment at Penn in imaging or another department dealing with imaging? And I came up with, what, I don't know, it's like 15 people here. But I'm sure I omitted people. This morning, Alan McLaughlin is here. He's not on the list. Meyer Chenard's not on the list. So this is an incomplete list. But in addition to this, as I said, there were hundreds of people who've gone through his laboratory, who've populated universities around the country and around the world. As I mentioned, he treated everybody the same with the exception of these two individuals. And he really viewed Mildred and Britt as his parents. And he would do anything for them, as you can see in this next slide. He would climb into... there should be one more. This is when the magnet was being delivered to the swimming pool. I doubt that what Jack created in the basement of Blockley is going to be replicated soon or ever. I don't. It was very, very unique. He was truly the Pied Piper of imaging research. Young people loved him. Older people respected him. It was more than once that I had to convince a young trainee to go back to school and get a degree because all they wanted to do was stay and work with with Jack, and also Britt and Mildred. But he would bring people in. Many of them were college graduates. Many of them started work with him when they were juniors in college and never wanted to go back to complete their degree. They had such fun working with him. And it was not infrequently that I would sit down with one of these younger people and say, you know, he is wonderful, but you have to get your degree and then go back and work with him. And some of them did. Some of them then went back, got a degree, went on to medical school, and then went back and worked with them. So he was a very, very unusual, very, very special person. And everyone, not only at Penn, but I think around the world, have had an opportunity to work with someone like Jack are going to be missing him a great deal.
Well, it's a pleasure to be here. I'm Nick Bryant, and I succeeded Stan, and I am the current chair of radiology, and it's very good to see all of you here, and for me to meet many of you who I've heard about for years and years. I've been here 9 years, but I'm obviously the new boy still in relationship to this audience, both to Penn and to Jack Leigh and his heritage. It's very interesting that Stan's experiences and mine have certain similarities. Jack is one of the two scariest people that I ever met here at Penn. And that's pretty tough competition, because when I first came, Bill Kelly was still the dean. But Bill was nothing compared to two of the people in our department. So about the second day I was here, I was called by Dr. Chance to his office, just as Stan had been called to his office. And Britt told me how things were here and what I should do, and I've done my best to follow those orders since then. Jack I had heard of and had seen at meetings, but did not know. But Jack was on the top of my list of the senior faculty that I really wanted to meet. And I didn't know at the time, but as you can imagine, Jack did not call or order me to do anything. I decided after a week or two that I would call over and make an appointment to go and see Jack. So I called over one morning, and someone did answer the phone, but it wasn't Jack. He said he wasn't there, and I didn't want to leave a message. I wanted to be deferential to Jack's seniority. I said, well, I'll call back. So the next morning I called, and they said that Dr. Leigh wasn't there. I said, I'll call back. So the next morning, I called again, and by then I gathered the word had gotten through the lab that the new chair was calling for Dr. Leigh, and then Susan somehow or other intercepted the phone call and subtly said it would be more likely that I would be able to talk to Dr. Leigh if I called in the afternoon. So the next afternoon, I called over, and Jack was there and answered the phone, and I said, Dr. Leigh, I would very much like to come over and meet you and talk to you. And there was this moment, he says, why not? I said, okay, I'll come over tomorrow afternoon. And I'd never been in the lab before, so you come off the elevator into the old lab, and I had been prepared that this was a different lab. But I wasn't quite prepared for the large room with 20, 30 desks there, no offices. And I wasn't really prepared. I knew what Jack looked like because I'd seen him at some of the meetings, but to find him in his white unbuttoned shirt, blue jeans there in the middle of the room at this desk with papers all around him, caught me a little bit by surprise. So I walked over at his desk, I introduced myself, and sort of being sort of direct and businesslike, I said, what are you doing? And he said, not much. And I could kind of tell that this conversation was not going to be a real easy conversation. And I said, well, what are some of the projects, the new things that you're working on? He shook his head and he says, why don't you ask them? And he obviously was motioning around the room. And it was pretty clear that that's the way Jack thought about the work in the lab. It was the people, it was the colleagues, his students in the lab, that was the work in the lab. It was not his work. And so basically I had to kind of motion to people from around the lab whom I didn't know to come over so that we could talk about something, because Jack was not going to talk to me. And so I think Robbie came over and talking about T1 row, and I think Sridhar Shangula was in there. We talked about oxygen. And so all these people came and we talked, but it was through Jack's colleagues and students, not Jack. I did not long after that, that Jack, under certain situations, would in fact, if you will, take credit to work done by he and his colleagues. And that, of course, could be exampled by a certain patent that tied up an army of lawyers, both from GE and the University of Pennsylvania for many years, related to work done in the lab. But getting to know Jack in his mature years was a real pleasure for me. He did remain one of the two scariest people I've met here at Penn. The loss of Jack is, of course, a huge loss to the Department of Radiology as well as the rest of the institution. The list of Penn faculty that Stan had up there, 8 of those were primary appointments in the Department of Radiology. And the Department of Radiology here, through Stan's efforts, has grown into one of the outstanding academic radiology departments, and there is no doubt that MR has been the real scientific strength of the department, and that's through the work of Jack, Britt, and the colleagues from the MMRCC. And the Department of Radiology cannot express enough appreciation to Jack and all of you who have contributed in that fashion. The loss of Jack is only part of the loss to the department from that lab. This last year has been a pretty tough year for the lab and the department. Only about a year ago, one of the outstanding young students of Jack's and the lab, Sridhar Shangula, died at age 35. He was one of our outstanding young clinical investigators. So the lab and the department will really miss these people. We will be having an open house in a couple of weeks where we will name the new 7T lab, the John S. Leigh resource for high field imaging. And so any of you who get a chance to come back to that open house. The 7T instrument is an impressive instrument. I was one of the first people in it. I have beautiful pictures of my brain, functional MR. It's the first instrument, MR, that I hesitated to go into. But I felt nothing, by the way. So if you're over at the open house and you get a chance, don't hesitate to go in the magnet and get a scan. It's a very, very interesting experience. The losses, the transition in the MMR-CC have had intellectual, but also psychological, emotional effects on the department. And I do have to thank Robbie Reddy for his key role over the last year in terms of dealing with these changes in the lab. Robbie has a special relationship with the current people in the lab, was very, very helpful in dealing with Sridhar's and his family at that time, and has been instrumental in the transition of the management of the lab as Jack's health has failed over the last year. And so, Robbie, I do want to thank you for all that you've done for the lab. So now we get the opportunity to proceed to the really fun part, to hear from many of you who have grown up and worked in the lab. I came in at the end of this process, and we're now going to go back to those people who were at the beginning of the process, Jack's intellectual parents, and I will now, not order, but suggest and ask Britt if he would come up and start with some comments about Jack. Dr. Chance?
Well, thank you both for a wonderful introduction to Jack's life, but I'm going to take you back to the start of his career at the Johnson Foundation, where the head of electrical engineering, Chris Brainerd, with whom I had collaborated with the mechanical differential analyzer solutions of enzyme kinetics, said he had an unusual student in his undergraduate classes who was obviously bright, but obviously didn't want to do what the teachers wanted him to do. That was Jack Leigh. Well, we talked for a bit as to what to do, and I said, well, why don't you send this young fellow over so I can talk to him? Well, in 10 minutes, I found that Jack and I resonated at the same frequency, which was radio frequency, and that this was a guy who was well worth saving. The problem was that he knew the material but didn't profess to his teachers that he did, because he wanted to do a different solution, as you might expect. Well, at that time, Jack showed proficiency in electronic circuits well beyond his years, and while I was pretty well set up with C.C. Yang and others, Mildred was struggling with electronics, and I thought that, Jack, you should work with Mildred. And he said, okay. And so that started Jack's collaboration with Mildred, which she will tell you about. However, some years later, in a rather beery session in Copenhagen, George Rada and I decided that we should investigate phosphorus magnetic resonance in human beings on the basis of our studies of a hedgehog with Rex Richards and Peter Stiles and others at Oxford, showing that indeed we could do biochemistry. with NMR of small animals. How about big animals? Well, George and I started simultaneously on this journey to make a human subject phosphorus NMR machine, and it was a friendly race to see whether Oxford or Philadelphia would get there first. And I immediately called upon Jack Leigh because I knew of his RF experience and his working habits, unusual, but very effective. So together with Roger Wheatley, who got us a cryogenic magnet with a 9-inch bore, hadn't been built before, and was soon to arrive, one at Penn, one at Oxford. Well, Jack took the bits and pieces of high-frequency radios and together with John Sorgi and Scott Elliff on software, put together a remarkable machine in the clinic of the hospital, which began to produce remarkable results. Scott Elliff, who's here, may tell you that it maybe illegally prescribed a therapy for a cytochrome B deficient young lady to bridge the gap in her electron transport chain with metadione. And as my last visit to her in Seattle, she was able to do the laundry, drive a car, and have a boyfriend 30 years later. So that was just the start of many fruitful researches, and I took the trouble to count up in the first 7 years, over 500 refereed papers were published, a number of them in PNAS. It was simply flowering of the technique without which wouldn't existed except for the efforts of Jack. Well, since then, I followed Jack's exploits, and wherever he went, it had a novel flair. Perhaps his studies of very fast reactions with Les Dutton were the earmark of this. In order to continue our interactions, I made weekly visits to Jack, of course, at 6 o'clock in the evening, not at 9 o'clock in the morning. Thank you very much. And Jack always had something exciting to say. It was either a paper which was all screwed up or a paper which was uniquely good. And so we continued that until I left for Singapore and unfortunately didn't reactivate them. But I can assure you that every contact with Jack is worthwhile. He has something to give you that nobody else could. And so we treasure his memory as one of the flowers that grew at Penn and touched the lives of many, many. Thank you.
All right, let me get this in my pocket.
Okay.
Yeah. Thanks. You've heard about Jack's career and his unique features from the earlier speakers, and I'm going to talk not so much about his scientific work, but what kind of person he was. I first met Jack when he was an undergraduate, an electrical engineering student, as you have heard, and I had just come to Penn, and I was chagrined to find out that there was no NMR instrument at all anywhere in the university. The Johnson Foundation had an ESR instrument, and they had Jack. Britton Chance was very supportive of my research. The best gift he ever gave me was assigning Jack to work with me. Jack, I found out, was capable of building instrument, not a high-resolution NMR, but I was interested in measuring the relaxation times of the protons in water, because at the time I was working on enzymes of ATP. I had already published the high-resolution spectrum of the phosphorus in ATP. I was interested in metal ions, and if I used metal ions and measured the effect of, for example, paramagnetic ions on the proton relaxation rate of water, I could find out how many waters were still in an enzyme ATP metal complex. I was rather naive about the whole thing, but I thought that could be done. And so Britt said, I have a young man who can construct such an instrument for you. And that's how we got started. And of course, there was no commercially available instrument at the time. And it took Jack, I will say it took him, he was still an undergraduate the first year. That was 1960. It took him a year to build the thing for me, but it worked. And that was really quite an amazing feat for a young man who was still an undergraduate. And I was impressed. But I was impressed even more with the kind of mind he had. He was a nonconformist, absolutely, questioned everything. And he had the remarkable combination of having very imaginative ideas and at the same time a tremendous practical knowledge. Through the years he worked with me, altogether 11 years, the last 4 as a graduate student. He got a PhD in biophysics under my mentorship. But during those years, just to give you some examples of his practical knowledge, he first of all, he succeeded in building, constructing this a spectrometer that could measure relaxation rates of protons, which was quite a feat. And then at one time, I wanted to we finally got an NMR machine, a high-resolution one of our own. I should tell you that that was a 60 megahertz instrument that Varian manufactured. 60 megahertz for protons. And one day I decided I wanted to see if I could spin in the Varian probe at the magic angle and sharpen the lines in a protein. And I told Jack that, and one of the things that was required, of course, was a synchronous motor of very high speed. And I hadn't the least idea where one could get such a thing. And Jack immediately said, a dentist drill. That was typical of the kind of thing he would think of. And then when we finally, many years later, got the first superconducting magnet, it was a 220 megahertz instrument. It was the first one in a university. The first one went to DuPont, the second one went to Bell Labs, and we got the third one, which we only got by having a consortium of investigators to apply for it. In those days, NIH didn't give an individual an instrument that cost $250,000. In any case, Jack was put in charge of this, and it had a real flaw. The magnetic field was not constant. It wasn't stable. And Jack looked at this instability and decided that it was probably due to the trolley car that ran underneath the building where the instrument was housed. Well, he wanted to prove it. He needed a magnetometer to follow the 24-hour schedule, and I tried to get him a magnetometer from the physics department, the chemistry department. Nobody had a magnetometer. The archaeology department had a magnetometer. And sure enough, Jack found that it followed exactly the schedule of a trolley car, because from midnight to 5 in the morning, the trolley car didn't run, and then the magnet was perfectly stable. He not only diagnosed the trouble, he knew how to correct it. He constructed a circuit that would take care of it, and the engineers at Varian were very interested in this because they had just sold a similar instrument to the University of Chicago, and they had the same problem. They had the subway running under the building, and they didn't know how to solve it. When Jack told them he had solved it, they wanted to know how Jack had solved it. So he did some hand-waving and so on. He was teasing them, not telling them how he had really done. And finally, he had pity on them, and he told them. And they gave him, as a gift in return, a magnetometer. That's the kind of thing Jack was always doing. On the other hand, as far as his imaginative ideas were concerned, by the time he got his PhD, he had published 8 papers. 3 of them he was the sole author. And the span of these papers, all 8 papers, each of them was in a different journal. The first one was in the Review of Scientific Instruments, and was a new way of measuring magnetic fields. The other 2 were theoretical papers. The first one was based on some experiments another graduate student and I had done with 2 paramagnetic probes. The ESR spectrum, the effect of one magnetic probe on another, it was manganese on a free radical that had been attached covalently to the enzyme we were interested in, and the effect of the manganese on the line shape of ESR. It was a very unexpected result that we had gotten. There was no change in the line shape. Instead, there was a diminution of the whole spectrum. And we puzzled over it, and I certainly couldn't figure out how that had happened. That was unexpected from the theory at the time. Well, Jack thought about this for a while, and he wrote a paper on the theory of this effect, which gave the right answer. And incidentally, it was a way of calculating the distance between the 2 paramagnetic probes. This paper had 241 citations. Now, for a student who he had by this time become a graduate student, to write such a paper was really quite remarkable. The other paper that he wrote on his own was the effect of chemical exchange reactions on a solution of that effect on the relaxation times. And that had 111 citations. All this before he had his PhD. Now, he really, in addition to this combination of practical knowledge and very imaginative ideas, he had other characteristics that were unique. And one of them, of course, was that he just abhorred pomposity in anyone, and he also couldn't abide bureaucracy. And sometimes some of his irreverent attitudes to the powers that be was not very well appreciated. And many times he was not very tactful about talking about these things. And I remember one time he'd been working with me for about 3 years at that time. He had done something very unorthodox. I don't even remember what it was. And I told him that such behavior was not acceptable. And he said to me, somewhere there should be a niche for a person like me. And he found that niche, and as you all know, it worked beautifully for him. He had, in addition to the nonconformity, things happened to Jack. He had this charm, which was unconscious on his part, and he charmed people, and things happened to him that happened to no one else. He was particularly fortunate in exerting this charm, unbeknownst to himself, I'm sure, on the female population. I remember he had, at one time, when he was in charge of this NMR facility, this was after we had the superconducting magnet, and he had begun this habit of not appearing at 9 o'clock in the morning. I must say the first 5 or 6 years he worked with me, he was there at 9 o'clock in the morning. But when by that time, the time I'm talking of, was after he had his degree, and I should say that the department appointed him an assistant professor as soon as he got that PhD in 1971, because everyone recognized how unique Jack was and how much of a contribution he made to the whole department, not only in the NMR facility. He began coming in later and later. First it was 10 o'clock, and then it was 11 o'clock. And sometimes I would call down there about 10 o'clock and ask for Jack, and his technician would cover for him. She said, "Oh, he just stepped out." And I knew very well that he just hadn't appeared yet. And so it went. But things happened to Jack that happened to no one else. For example, when he was, before he became a graduate student, when he was essentially an electronics technician for me, he was invited to appear in Who's Who in America. At that time, he had 2 papers that he had published, and inclusion in publication of that particular reference is usually reserved for more senior people. But there was Jack, and what did he put in there? He put in the fact that he had been on the football team at the University of Pennsylvania, and so on. And it got published. And another example of that sort of thing is when he became an assistant professor, and upon getting his PhD, and he'd been here a couple of years, the senior faculty in the department decided that Jack should really broaden himself. He'd spent all his time, his whole career up to that point, in the Johnson Foundation. So it was suggested to him that he take a sabbatical and go somewhere else in the laboratory. Well, Jack decided to go to Cambridge, to the MRC unit in Cambridge University, and he applied for a Guggenheim, and he got it. Now, that was even more unusual, I think, than getting into Who's Who in America, because that is really reserved for rather senior people. But Jack, having been an assistant professor for 2 years at that time, was awarded a Guggenheim Fellowship to go to the University of Cambridge. At Cambridge, he met Judy, and one of the wisest decisions he ever made was to marry her. And he came back with a wife. As Jack, outside the lab, he had many, many interests. His interests outside the lab are almost as broad as his interests in science. By the way, his interests in science covered a terrific range. He was interested, for example, in why snowflakes had the kind of pattern they had. He was interested in how prions really worked. He was interested in the fundamental problems of quantum mechanics. And In his outside interests, he was almost as broad. He was really interested in many manifestations of nature. One of the things he was interested in were plants. He grew plants. He was very successful, particularly with gardenias. He was also interested in wood, in various shapes, and he was interested in driftwood, and he was interested in wood with various patterns. And not only, just as he was a practitioner with the plants, he was with wood as well. He was an excellent craftsman and made many, many things out of wood that were aesthetically very pleasing. And he made a record, a daily record of all the climate conditions. He kept meticulous record of the temperature every day, of when snowfalls occurred, and when certain thflowers and bushes started blooming. And he had a continuous record of the year, so you could ask him, what in the year 1981, how many snowfalls did we have and when did they begin? And he could tell you. He had a fabulous memory, anyhow. He was a voracious reader, and he read everything. And if you asked him a question about something in the literature, he could not only remember it, but fish out a reprint from his chaotic desk. He always could find things. And another thing that he was interested in was language. He loved strange words. He taught me several of them. He loved strange combinations of words, such as, I knew of a Mr. Coffin who lived on Cemetery Avenue. That delighted him. And he collected those and interacted with some of his former friends with words and expressions that are better not talked about in polite company. But and in addition to all these things that he was interested in, he had a very unusual conversation. His talent was in interaction with other people. He was really very compassionate and kind, and tried to solve the problems of people who had problems. On the other hand, he could be very offensive. For one thing, in many cases, people he had been very friendly with, once they were out of his environment, out of sight, out of mind. I mean, it was really I never understood quite why this business of being away from him did this to him. On the other hand, as has already been mentioned, he didn't care about the status of anyone. He only really objected to scientists who are more interested in shining than in science, those who put their ambition above their interest in science. Those people he really disliked. And his greatest talent, I think, was his conversation. I'm not talking about gossip or anything of that sort, but his scientific conversation. When Jack would engage in a conversation with any listener that he thought had the intelligence that he could respect, it was marvelous. His mind was so fertile, the ideas would just pour forth, and it always reminded me of the two characters in James Stephen's book, The Crock of Gold, the two philosophers who felt that the more ideas they gave away, the more ideas they had. He also had their philosopher was, he was a sexist obviously, who thought the more ideas they gave away, the fewer they would have. Well, Jack was certainly of the first school. He just gave away ideas and they kept coming. No, they weren't all brilliant, but many of them were. He was the kind of person who had, when he had such a conversation with you, and he often did, as I say, it didn't matter whether you were a student, a technician, or a senior professor, he treated you as an equal, and he kept pouring forth with these ideas. And he enjoyed that so much, this interaction on an intellectual level, that I think that was his greatest talent. And I can say he was a great teacher from that point of view, one-on-one. And I must admit that I learned much more from him than he ever learned from me. And I think his impact on all the people that have interacted with him will never be forgotten by any of them. And they will never find such a unique personality as Jack Leigh. That's my problem.
Yeah.
Thanks.
It's okay.
So by way of getting serious now, Mildred and Britt used to pay Jack and me for this kind of activity. So in introducing the next session, I'm going to touch on the ESR machine that Mildred talked about there, and but not go into any details. George will do that. This photograph was taken late at night, and probably George, Jack, and myself were the only ones there, solving the world's ESR problems. But I'm going to just emphasize, I think, Jack's artistry and craft, amplify what Mildred, I think this is it. No. Can you move it on, please? I want to focus on, go back one. I want to focus on the fact that I learned how to blow smoke rings with Jack, smoking his White Owl cigars, 5 cents each. And I should be on Stan's list because this talent is hard won, and Jack spent a lot of time training me. As you can see, I'm struggling with mine. My mouth is still in an O shape, and there's smoke everywhere. But Jack seems to be able to generate a smoke ring without even apparently smoking. There's no evidence of a cigar anywhere, nor is his mouth in any particular odd shape. But this picture emphasizes the fact that Jack worked late at night, and Mildred's ESR machine was crucial. And as I say, this picture is full of Jack's inventiveness, apart from the smoke rings. But Jack, if we can move on one. I think I've got the wrong one here. No. I want to talk a little bit about Jack's craft and artistry, because he was strongly interested in this kind of thing, and we all his friends, do own wooden objects crafted by Jack. Next one, please. So Jack and I love to, that's jump 2. Can you go back one? This is a problem. Okay, go on then. Jack and I love to draw. We draw a lot of people in this room, and especially Mildred and Britt. Jack here is seen in a very characteristic position that was mentioned by Mildred, sitting down, reading the literature. He did read everything, and if people wondered what he was doing in the mornings, he was at home reading the literature. And when he came to work, Mildred provided rudimentary desks for him. Maybe that's where he learnt this ability to exist with almost no furniture facilities. Next slide. Jack had to actually have a sign that told people where he sat, and because the desk was so rudimentary. Next slide. Jack also had another side to him. We've heard terrifying rude, loving. He was also sensitive. And he's saying here, if you disagree with me again, I'll sulk. So he could sulk. But these are my pictures, but he himself showed a real talent, a real good handling of line to draw other people. Next slide. So we have hundreds of pictures done during the years. And this is one he did of Mildred. Next. And here's one of Brit. Next one. Wasn't very good at mouths. Next. And again. This is one of his best. He was also very good at social commentary. A Mexican graduate student whose name I can't remember, unfortunately. Next slide. This is another Jack commentary. Next. And he was very good with, as I say, line. This shows 3 pictures of the same person. So next. This is a Russian scientist. He still visits us, and his son has actually got tenure as an associate professor in our department, Andrei Vinogradov. Next slide. Shows, you see, social commentary of the times of the early 70s. Next slide. And here's a picture of George. So the 2 speakers today, because Jack loves smoke, it made drawing easier. So the 2 speakers today also were not safe from Jack's drawings. Next slide. And this is all George Reed. Next. 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 And here's a picture of Jim Norris. It had your name written on it, Jim, so I fished it out. That's by Jack. Next slide. This one is by me. And next. And this is Walter, who'll be chairing the next session. So we've had all these pictures framed for the people, and I'll give you them as we go along. So the first, it's my honor to bring George back to talk to us here at the University of Pennsylvania. And he's going to talk about Jack's early contributions to ESR, many of them using that E3 variant that Mildred had.
Okay, it's a pleasure to be here, and Mildred asked me to talk about Jack's early contributions, and I realized when I got started that this is quite a daunting task because he had so many of them. And so I've selected just a few to tell you about. And the other thing is that I can't begin to tell you how important Jack was for my career and how much he taught me about magnetic resonance in general and EPR in particular. So if I can make this thing move, whoops, you got to go back. There we go. One slide forward, maybe. Take it forward, please. There we go. This is what I'm going to try to cover today in the way of Jack's early contributions. I'm first going to show you some images that remind us of Jack, and particularly me of Jack. And then I have in the pages of my textbooks and in files in my file cabinet, I have a number of handwritten notes that I kept from Jack explaining various things to me. And then we'll look at Jack's early bibliography and some examples from the papers that he published. And then we'll look at examples of his invention and more examples of his contributions to EPR and a few on NMR. And then finally, I'll share with you the last email message that I got from Jack in January of 2003 that dealt with the manganese EPR and galaxy formation. So if we can go one slide forward. When I first came here, this was a facsimile of Jack's transportation, a 1951 Ford. This one is in better shape than the one Jack was driving. The interior upholstery had deteriorated, so there were fringes hanging down here between the front and the back seats, and the springs were exposed in the seats. And he squeezed a lot of miles out of this vehicle. And next slide, please. Then he graduated to a Ford Mustang. And I managed to find a picture of a '64 Ford Mustang on the internet that was somewhat resembled Jack's vehicle. This one I noticed, though, has all the seats still in it, which the last time I rode in Jack's Mustang was in 1991, and there was no seat in the passenger side here on the front. But then when I came here in 1993, this car had been retired, and he was driving a modern Ford Explorer. Next slide, please. Okay. This also, I took this yesterday morning. This is a picture of the Richards Building, and I was impressed. It was 40 years ago this week that I started to work for Mildred as a postdoc, and these trees weren't nearly as tall as they are now. The trees have really grown. And this is the 6th floor Richards Building where Mildred's lab was, and this is where I first met Jack and our interaction started. Next slide, please. Okay, so these are some of the images that remind me of Jack. He had a number of versions of this briefcase. They all look similar to this, but they got a little more raggedy as time went on. And if we looked inside the briefcase for the tools that he brought to work, there were usually a couple packages of White Owl miniatures, a yellow notepad, sometimes he had white ones, and a black felt-tip pen. These were his tools. I think he used to carry a thermos full of coffee, but I didn't put one in here because I was afraid it would spill. Next slide, please. Okay, so this is some early notes from Jack. There's probably 38, 39 years old. I asked Jack how a klystron tube worked, how it generated microwaves. And he sat down with his pad of paper, and this is a pretty tattered piece of paper now, but it's precious to me because he drew out the circuit diagram for a klystron tube, including the filament voltage, and the filament current, and how this filament gave off electrons when it was heated that were accelerated by a positive voltage here on this beam. And then there's a hole in this beam that some of the electrons pass through, and then they get turned around by a negative voltage on this reflector plate here, and they set up a resonance going back and forth between these two devices, and that gives off microwaves. You can see Jack's microwave arrow coming off here. And he also explained how the mode sweep worked on the EPR instrument. There was a horizontal sweep on the oscilloscope was hooked to this reflector voltage, and a sawtooth pattern applied to it, and so that swept the frequency, or the voltage, and therefore the frequency, resonance frequency of the instrument. And these are the modes that one would visualize that were the resonant modes for the klystron tube. This is back in those days. These diagrams didn't exist on the internet. Today you can find nice explanations on the internet, but Jack was Wikipedia before there was a Wikipedia. Next slide, please. I showed Jack some notes that I had made when I was a graduate student deriving the block equations in the rotating frame. There were 3 or 4 pages of ugly algebra. He says, oh, you can do that intuitively by just using an analogy with chemical kinetics. And so this is the page the piece of yellow paper I saved. These are Jack's handwritten notes on the derivation of the block equations in the rotating frame with the analogy to chemical kinetics. There's 1 over T2 here. He has the rate constant K2 associated with it. So he knew how to do this intuitively, and he was quite conversant with these block equations, as we'll see in a little while. Next slide, please. Now, this is a table that Jack constructed dealing with dipole-dipole interactions between various magnets, unpaired electrons, as well as nuclear spins. And you can look at this table and see which are the strongest magnets and which are the weakest, and what their effect on a neighboring nucleus or electron would be at a 1 angstrom distance. And made several copies of this and distributed it throughout the lab, and I kept one of them in my research notebook just so I didn't have to go through the calculation. And Jack was as we'll see, was an expert in dipole-dipole interactions. Next slide, please. So we'll look at some of the many papers that Jack published in the early days, and I arbitrarily assigned a cutoff date to 1973. And I'm only going to be able to talk about a few of these, and particularly ones that I have some knowledge of the history behind. And so I don't want to slight the other people that are represented here as co-authors. So next slide. The ones, back one. We're going to look a little more carefully at the ones that have been annotated here with an asterisk. Next slide. This is another page of Jack's papers from that era, copied from PubMed. And next slide. On this list, we're going to talk about this particular paper. And then there are a number of publications that did not appear in PubMed. Next slide. These are primarily papers that appeared in physical journals like Review of Scientific Instrumentation, Journal of Chemical Physics, JPhys Chem. And we'll talk about, in particular, ones that are annotated. Next slide. Yes. Next slide, please. There. We're going to talk about these contributions as examples of Jack's ingenuity. Okay. Next slide. Mildred introduced this topic earlier. This was a table from the early paper in Nature that described the enhancement of water proton relaxation when a paramagnetic ion such as manganese was bound to a macromolecule, like creatine kinase. And here the manganese comes into the realm of the protein through its complex with ADP. And this is really a classic paper that introduced a lot of things that are used in magnetic resonance contrasting and everything today. So this was a spectacular achievement. Next slide, please. So this is a famous paper by Jack that appeared in Journal of Chemical Physics. He was the sole author. He was still a graduate student at the time. And what he did was he modified the theory of dipole-dipole interactions that had been elaborated by George Pake 20 years earlier. This is the 60th anniversary of Pake's landmark paper in J. Chem Phys. He elaborated on this in the interaction of two spins in a rigid lattice, but allowing one of these spins, he marked it R here in his diagram, to relax rapidly, and what the influence of that relaxation would be on the line shape for the spin that wasn't relaxing so rapidly. And next slide. This was his formalism. He wrote off a powder pattern that had an orientation-dependent line width. And the orientation-dependent line width depended ultimately on the distance between the two spins. And he simulated spectra for a nitroxide, immobilized nitroxide spin label with various distances. And these spectra showed what Mildred referred to as the lines were not uniformly broadened, they just got weaker and weaker. They appeared to diminish. And Jack rationalized that there was a fraction of the spins that were close to the magic angle in this rigid lattice setup. And that window that was more or less unaffected by the strong dipolar field from the manganese was smaller and smaller the closer the manganese got to the spin label. And he developed some diagrams, some graphs where one could read off this parameter and easily calculate a distance. Next slide, please. So this was the paper with June Taylor and Jack and Mildred that appeared in PNAS that described the application of this theory to determining a distance between where manganese ADP was binding and where the nitroxide spin label had attached itself to a thiolate group. And by matching this up with the graphs that Jack had developed in the J-Chem Phys paper, next slide, the distance between manganese and the nitroxide radical, 8 angstroms, was determined. So this is one of the first examples of using relaxation between two paramagnetic species to determine a distance in a macromolecular complex. Next slide, please. This has evolved over the years, and now we have these marvelous pulse CPR experiments that perhaps Jim Norris can tell us about. This is double electron-electron resonance, and this one, I like the acronym, RIDME, is relaxation-induced dipolar modulation enhancement. It's quite a mouthful. But these pulse CPR experiments allow us to look out theoretically close to 75 angstroms distance and see weak dipole interactions between two paramagnetic species. And this particular example was an enzyme we worked on called pyruvate ferredoxin oxidoreductase. There's a free radical generated here from hydroxyethylidene TPP. Free radical is delocalized, and in the generation of the free radical, an electron is moved out into the chain of iron-sulfur centers that are also in the protein. And the question was, which of the iron-sulfur centers is reduced to an S = 1/2 state when this radical is formed? And the answer coming from these experiments was that the reduced iron-sulfur cluster is this guy right here. Next slide. Okay, Les introduced the smoke ring topic. I'm so glad I had my camera with me that evening. This has a number of things that I want to bring to your attention. When Mildred and her consortium first got the 220 megahertz NMR spectrometer, filling the magnet with liquid helium was quite an elaborate task. You put the can of liquid helium on a jack, cranked it up to the level of the top of the magnet, and then there was a rigid tube that went from the magnet to the can, which transferred the helium into the magnet. And Jack didn't like that setup. It was not easy, and I think he convinced the Air Products people to build him a flexible transfer line, so he didn't have to raise the can up to the level of the top of the magnet. And so this transfer line, which resembles most of the transfer lines we have with our low temperature cryostats nowadays, I think Jack had a fair amount to do with that design. And then Jack realized, hey, we could use this to do low temperature EPR. So he would take this from downstairs, bring it upstairs at night, and use it to put liquid helium into the bottom of an L-shaped dewar, which he convinced Jim Scanlon to build in his garage. And thereby get a temperature where EPR would be visible for things that normally relax very rapidly. So this transfer line here is one of Jack's legacies. He also was ingenious, improvised. He used the lens out of the overhead projector here to focus the light beam on the cavity for the experiment. So the overhead projector that was in the Johnson Foundation Library was disabled for the duration of this experiment. I also noticed a couple things here. This is the attachment of the transfer line to the top of the helium can is through an extension cord that's been tied in the top. He used whatever was available. That's typical. I was also present in the lab one evening when Jack tipped one of these cylinders over and broke the top off, and that was pretty exciting. He didn't follow the safety regulations of having the cylinders tied up all the time. Now, a lot of Jack's contributions then during this period of time dealt with low temperature EPR studies, studies with Tomoko and with Dave Wilson, and it was the advent of this innovation in doing liquid helium EPR that made those things possible. Next slide, please. So we get back to the smoke rings. I looked to see if there was some scientific value to this experiment. And sure enough, in Wikipedia, next slide, it says that smoke ring is a visible vortex formed by expelling smoke through an opening. And then, next slide, it says that it usually takes a lot of practice to learn how to do it. And Jack and Les had a lot of practice. Next slide, please. So this paper was submitted in 1969, and Jack and I were here late at night. Takashi was here usually late at night as well, and we bootlegged some collaborations that turned out to be really a lot of fun. Takashi's people, Henry's here in the audience today, and Mike Waterman and Toshio had generated heme proteins that had manganese protoporphyrin in them instead of iron. And they gave these rather bizarre-looking EPR spectra. Bizarre if you're thinking in terms of manganese, because they do resemble very much the G6 and the G2 signals that iron has. And in the process of these studies, we had convinced Takashi to allow us to use his 35 gigahertz EPR instrument. And we thought it would be interesting to look at one of these complexes at 35 gigahertz. And the experiment was difficult because getting low temperature in that particular setup was really a very difficult task. And Jack and I worked most of one evening to obtain this spectrum. So this is a liquid nitrogen temperature spectrum of the manganese protoporphyrin complex with cytochrome C peroxidase. And when we turned the magnet on to start the scan, there was this huge signal came out. Right as soon as we turned on the field, something's wrong. So we did it over and over again, and Jack started laughing because he understood what was going on here. And next slide, please. What we had managed to accidentally do was we had matched the microwave energy with the splitting of the Kramer's doublets in the S equal 5 halves manifold. So this was a almost zero field EPR spectrum. So we measured the zero field splitting directly by matching accidentally the microwave quantum with the Kramer's doublet splitting. Next slide. Next one. Another project that turned out to be really useful was Takashi made a bunch of nitric oxide NO derivatives of heme proteins. And he recognized that by looking through the unpaired electron that was somewhat localized on the NO group, one could peek through the DZ squared orbital of the iron and see what was down on the other side. And this was before we knew whether there were histidines there or what. And so we went, Takashi ran a series of spectra, beautiful spectra, including some using nitrogen-15 labeled NO. And we were able to determine for a number of heme proteins what the nature of the ligand on the bottom was. Next slide, please. One of the complexes that gave a particularly beautiful result was horseradish peroxidase. And here you see complete isotope editing. And this was done back about, when was this, 1971, Takashi? 70 or 71. A nice isotope editing experiment. You see 3 G values for this EPR signal. The splitting in the middle, the big splitting right here, is due to the nitrogen-15 on the NO. Then there's a triplet splitting of those signals that's due to the nitrogen-14 from the histidine ligand that's on the bottom. And then Takashi also made the iron-57 version, so there was an additional splitting from the nuclear spin of the iron in the iron-57. And finally, he used iron-57 with nitrogen-14 instead of nitrogen-15, and you get this really complicated pattern, which we could decipher in a straightforward manner. Next slide, please. So in the process of doing these experiments, Jack thought it would be interesting if we could squeeze some more resolution out of these X and Z components of the EPR signal. And so he instrumentally obtained the second derivative spectrum. You can see the improvement in the resolution. This was, in fact, a triplet on each end. And this got us started doing resolution enhancement. And when I visited here in 1991, Jack taught me how to do Fourier filtering for resolution enhancement. It turned out to be incredibly useful for looking at free radical spectra that we've been doing for the last 15 years. Next slide. These are the block equations again. Jack published this paper in 1971. I don't know whether he had his PhD degree yet then or not. He published it in the Journal of Magnetic Resonance. He looked at the block equations that were modified to take into consideration the effects of chemical exchange on the T1 and T2 relaxation times. And he realized that this was a system, these equations formed a system of linear homogeneous differential equations, and you could solve them as an eigenvalue problem. And so he got some exact solutions to the block equations out of this little exercise. It's another example of his genius in seeing things that other people hadn't seen. Next slide, please. Well, I'm getting close to the end here, and I wanted to point out this particular paper. Alan McLaughlin's in the audience. When Mildred got the 220 NMR and it was converted to do pulsed Fourier transform, Jack was trying to measure T2s, and what he saw was a phase modulation of the signals under the influence of two pulses. And he characterized the accumulation of phase error here is due to the spin-spin coupling between the protons. And he told me later that he was this far away from discovering 2D NMR when he did these. He said he was just this close to doing a second Fourier transform. Next slide, please. Well, this is the email I was telling you about. It came in January. I'd been in a meeting. I came back and I looked at my email. Oh, Jack sent me an email. And the title here or the subject line was really intriguing. And Jack's emails always had little puzzles in them. Well, what's he going to challenge me on this time? And so here's his message. Check out figure 3. In the text above the figure, it says they use 600,000 CPU hours. I think that's about 70 years. So here's he attached the paper. Next slide. And sure enough, here's the text copied from above figure 3. It said they consumed 600,000 CPU hours, and I did the calculations. It's actually 68.45 years, but I'm sure Jack did this in his head. The next slide, please. Okay, so he wanted me to check out figure 3, and this was the subject line, manganese EPR and galaxy formation. So let's look at figure 3. Okay, here it is. This is the evolution of enclosed dark matter masses in the model galaxy at different radii. So this is a radii of a model galaxy. And there are two different simulations here. The solid ones are the ones I think I'm supposed to concentrate on. When I got down here to the bottom, I saw this 6-line pattern here. This did look a little bit like manganese EPR. So next slide, please. Here's that bottom trace copied again, the evolution of dark matter masses in the a model galaxy versus radii. And this is kind of a generic EPR spectrum of the manganese protein complex. And you see that Jack was reading this paper on evolution of dark matter, and he saw that he immediately recognized the similarity between these two traces. And it's a precious email that I'm going to keep forever. Next slide, please. So I've covered most of the things I want to cover. I just want to say, as Jack was apt to say, good on you for listening to me.
So Mildred mentioned characteristic of Jack that was out of sight, out of mind. But there were some people in the world, special people, who held his great respect, irrespective of distance. And one of them is Jim Norris, who we have today. Jim was early into the use of ESR, applied to redox systems and light-activated systems. And Jack and I have always respected Jim for what he did right at the beginning of this time. And we're fortunate to have him here right now.
Thank you, Les. I also would like to thank you for this privilege of giving a presentation at this symposium dedicated to Jack's memory. What I'm going to do today is I'm going to introduce part of my work, which is what Les asked me to talk about. It was my work, not Jack's work. I'm going to start with one-spin resonance EPR. And this is an introduction for the two-spin. And Jack's work involving two spins had a huge impact on my life. I think what he discovered, which must have been obvious to him by instantly looking at the spectra that he was recording, is not well appreciated in the world of chemistry today. And for those of you who would like to know more about this, you can talk to me later in private, because I'm not going to go into the subtle details that are so important. I could just mention that it has to do with current trends in science, nature, where people are trying to explain how birds navigate in the Earth's magnetic field. So Jack's work is an early stage of this formulation of the current models of bird flying, bird navigation, let's say. What I'm going to tell today starts, in effect, all the work I'm going to describe was done at Argonne National Laboratory. And it was, I was there as a postdoc, as a very naive postdoc. I came from Sam Weissman's laboratory and started working with Joe Katz. That was a dramatic change in environment for me. But then one summer, Joe left the laboratory to spend the summer with Glenn Seaborg. And then that's when I started having some fun and doing some research in the lab. And so I apparently like Jack, I like to do some reading of the literature and find those things that would excite me. And this shows a paper by McElroy, Fayer, and Mazzarell, which intrigued me because they clearly showed that the EPR signal that was observed in photosynthetic bacteria arose from a bacterial chlorophyll molecule in the system. This is back in the days when virtually nothing was known about photosynthetic systems. And they did it by comparing the kinetics of the optical with the kinetics of the EPR. Well, that was impressive, but what really intrigued me was the next phase of their work. They had some deuterated systems, and they compared the oxidation of chlorophyll versus the oxidation in the plant. And when it was deuterated, they found that the line width that they measured, and by the way, chlorophyll is a very ugly molecule. It has something like 1 million lines in it, and therefore you see no resolution in it. You can use all of the enhancement techniques that Jack was talking about, and you'll never see any additional lines in this system. It's just one ugly Gaussian line that you get. So you measure one parameter, that's the width of the system, and when it gets deuterated, of course, it narrows because a lot of the line width is due to the protons. And it turns out that the oxidized chlorophyll has the same reduction in line width as the in vivo system. But what really intrigued me about this was that the line width of the model systems, the oxidized chlorophyll, which is supposed to rise from it, was far from the line width that was observed in the photosynthetic organisms. And I have a quote down here from the Fair paper of what they claimed it was due to, an environmental difference. And I thought, well, boy, this must be one heck of an environmental difference. So I thought I would look into this a little bit further. So we had an algae farm at Argonne, which I could take advantage of. We had many different species of algae and bacteria that we were growing, and under various isotopic compositions, in fact, fully deuterated systems. So I did take advantage of this, but I looked at a variety of chlorophyll samples, and what I found was that you get line widths that are very broad, or you can get some line widths that are incredibly narrow. This is still amazing today. This is extremely difficult to do, to get systems that have such narrow lines in the system. And I attributed this to electron transfer. That is, you oxidize a system. These systems down here were aggregated. So upon oxidation, the whole does not stay stationary. It moves up and down in this aggregate. And it was fairly simple to make a model for this. It was because of the Gaussian line shape, it's fairly trivial to show that if you have a monomer of size n, its line width is related to the monomer line width by the square root inversely proportional to the square root of n. And if you have a dimer, or what we ended up calling the special pair that exists in photosynthesis, it's a square root of 2 relationship. This means that the line width will narrow by essentially 40%. And when we look at a lot of systems, that's what we found. We found that this is the observed system for a series of algae, a series of photosynthetic bacteria. This is the simple calculation. There's some theoreticians in the audience, so they may not want to call this a calculation. You just divide this column by the square root of 2, you get the second column, and this is just a ratio, and it worked out pretty well. But chlorophyll, it would be better if we could look at the individual couplings on the molecule. This shows the chlorophyll molecule A. Suppose that we're looking at this molecule, this particular site. You can do this with Indor. Indor is nothing more than the NMR of the free radicals. So we have a cation of this. This says that the coupling constant, the spin density at this site, if it's shared between 2 molecules, should be reduced by half, not by the square root of 2. So what we expect to do if we do Indor, we do Indor on the model oxidized chlorophyll and compare it with the Indor of the organism, we should see all coupling constants halved. And this is what we did. And this is one of our first attempts. I'm not going to dwell on this. This is showing that what happens is for bacteria, you can interpret all the data in terms of coupling constants that drop by a factor of 2. And then these spectra are being taken by a really pretty crude Indor machine that was sold by Varian in the early days, and these are fairly difficult experiments to do. This is the center of symmetry. There's every line that exists on this side, there should be a line on the other side, so we only have to look at half the spectrum for this system. We worked with a postdoc, Hugo Scheer, at the time, and we were able to isotopically label the chlorophylls and the organisms so that we could look at one particular, I wanted to go backwards, but I can't. This thing doesn't seem to go backwards. If we look at the chlorophyll molecule right here, we wanted to compare this particular site with that particular site in the in vivo to make sure that we're comparing the right sites. For example, suppose I was looking at this site in the chlorophyll molecule oxidized, but in the organism, I was looking at this site, and they happen to be related by a factor of 2. This is not good because this is not what we're predicting. We're predicting that every site in the molecule gets the coupling constant reduced by a factor of 2. So by making assignments in the system, we could settle this issue. So this is what we did. I should also point out that if you take this spectrum, this is for bacteria, if you take this spectrum and shrink it in to the center here, each coupling constant is represented by the Indor at this spot, should appear halfway in. You can just take this spectrum and like an accordion, squeeze it in by a factor of 2, and you'll more or less get the spectrum that's observed in vivo. So I thought we had pretty good evidence for this. You can look at these individual sites in the molecule that have spin density on them, and you can drop them by a factor of 2, and you find out that you can get aggregation numbers for the in vivo systems, and it turned out to be a factor of 2. So I gave up on this problem. I thought this was finished. And so I became interested in another problem, and this is where the work of Jack comes in. And the work of Jack, I want to point out, is important for what I've already introduced, because although it became quickly acceptable that our model for what was happening in photosynthesis, that is that the primary donor was not a single molecule, but was a dimeric form, which we call the special pair, because there was really something unusual about it, it became controversial again later. And I can use Jack's insight to help prove that we were right all along. So now this is the paper here that attracted my attention. There were several papers here during this time that attracted my attention that were due to Jack Leigh. And this shows the Pake powder pattern that was discussed earlier in the previous talk by George. And this is thermal equilibrium for a triplet state. And the triplet state splitting from this side to the other side is caused by the dipolar splitting in the system. And this shows how it is an absorption. This is absorption, 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 absorption. But when Jack and Les looked at the organism, and the clever part there was they worked out what was happening with the chemistry as well as with the spin chemistry. They showed that if you take the organism and you reduce it in advance, then you get this really unusual spectrum down here, where this line is now in an enhanced absorption, emission, emission, absorption, absorption, and emission. And this attracted my attention tremendously, and it still has a big impact on my life today. And I want to explain to you why this is the case here. Now, they pointed out several things in this particular paper, and I give Jack credit for this, presumably because this has to do with the intrinsities of the EPR in this case. First of all, he noticed that the splitting, the two extreme splitting between the system, was smaller than it is in model compounds for the chlorophyll. And this, he said, agreed with our prediction of the special pair. And this was the first independent from the cation story that there was a dimeric form of chlorophyll involved in the primary donor of photosynthesis. The second thing he pointed out was, which I would have never in a million years, I think, would have figured this out, is that this particular pattern of non-Boltzmann population is caused because only the middle level of the triplet state is populated, no matter how the molecule is oriented with respect to the magnetic field. Okay, so this was very, very important. And the third thing he pointed out was, because of that, this signal is strong. I used to tell people who visit our laboratory after I learned how to do this from Jack's work, that we could take a flashlight and go all the way across the other side of the laboratory and shine it on the magnetic resonance, and we would get a signal. It's truly a remarkable thing, the signal that you get out of the system here. And there's one other thing that I'll point out, hopefully a little bit later, about the signal. Now, so we launched a study on the triplet state, and just to show that they really did have a big impact on me in this case, the first 4 references in this paper are due to Jack. All right, so now on this particular slide, I'm pointing out that what we have in these systems is random order. Later I'll talk about single crystals. When you have single crystals, you only get 2 lines. When you have random order, you get an infinite number of lines essentially here. And so you get what's called a powder pattern or random order pattern. And this again shows the spectrum that exists, absorption, all the way across. And this shows the powder pattern that you get when you look at the photosynthetic organisms: absorption, emission, emission, absorption, absorption, emission. Now, what I realized when I tried to repeat what Jack had done, the claim was, correctly, that only the middle level of the triplet is populated. Now, physics becomes involved in this, and the physics says that typically, usually only one of these three sublevels for triplet, which has three triplet levels at zero field, gets populated. So you can see that if this middle level right here, which is T sub y, called T sub y, gets populated, it is true that the middle level gets populated. But if I come down to another orientation of the system up here, if the middle level is the one that's getting populated, the upper levels and the lower levels are getting populated. So physics is no good for this. And Jack was using, apparently, physics in his thinking at this particular time, but what we needed was some chemistry. And this just shows we looked at the chlorophylls for the triplets, and we looked at the organism. And you can see that the patterns are quite different. These signals also have emission and absorption, but you'll never find this particular pattern. So the purpose of this paper was to try to explain what was happening here. We looked at a variety of chlorophylls. Never once did we find for any chlorophyll the pattern that we always saw in a variety of organisms. So the question is how to explain this. This is the one with physics. I tried to show you, I had before, the purpose of this particular aspect of the work was to prove that it is impossible to get a pattern that matches what Jack saw as only the middle level of the triplet state getting populated. And so we just listed all possible combinations that the physics model would do. Later we developed a more rigorous proof of this that can be done with just simple quantum mechanics. But in any event, there was no pattern on here that looked anything like what Les and Jack saw on those nights making smoke rings, apparently. So this is what happens. This is a slide that I borrowed from Gerhard Kloss, a dear friend of mine who died about 10 years ago. So what they did, back then you see chemists, photochemists in particular, they did not know how to do good photochemistry at that particular time. They could do photochemistry from the triplet state, which this represents over here, but they couldn't do photochemistry from the singlet state that had a charge separation that lasted a length of time. So look, in their slide, they started from the triplet state with time and went to the singlet state with time. Now what this shows is supposed to show is we put one electron on one molecule and put the second electron on the other molecule. If both electrons are in the same molecule, they're strongly interacting with each other and they see essentially the same magnetic field. And so the precessional rate of the two spins matches. So in this particular case, if they're triplet, they precess at the same rate, they'll always remain triplet. If they're singlet, they precess at the same rate and they always remain singlet state. But suppose we put some distance between the two molecules, and in particular, because you put distance between them, and they're different molecules, let's say in photosynthesis, one could be a bacteriophyte and one could be a chlorophyll, the local magnetic field is quite different on the two molecules. Therefore, they precess at different rates. So as this one goes faster or slower than the other one, they slowly evolve back and forth between singlet and triplet. And because of this, if you create systems from a singlet state, they can only go to this particular triplet. Now notice if I add these two vectors together, I get a vector in this direction, and that's what the middle level of the triplet state is always. So no matter how the molecules were oriented in the system, the middle level of the triplet only got populated. And this is what was going on. And this is the diagram that they presented in their paper, which is amazingly correct, particularly for that time period in our understanding of photosynthesis. So this shows the starting. It has the two electrons. It goes to the singlet state. The electrons are still paired. But then it goes over to this radical pair. Because this chemistry is so incredibly fast, they're still paired at this point. All this is a conservation of angular momentum because it takes place so fast. Now notice they have a question mark. They didn't know whether it comes back. At low temperature, I think the evidence is strongly against it coming back, but at room temperature, this can happen. At low temperature, then the system goes on to create a T0 triplet down here. This is the middle level triplet where the electrons are both paired, but now they're on the same molecule. All they've done is use a charge separation. Now they return back to the original molecule that they're on, which is what they show in this diagram. And they also invoked the possibility coming down here. But invoking this pathway would also allow some situations in which both electrons are down and both electrons are up, and this was not observed to any great extent in the system. Now, this tells us several things about it. First of all, it says that the charge separation state was above the singlet state, above the triplet state. This meant that photosynthesis was doing an extremely efficient job of energy transfer, because when chemists could make the singlet state react, but they had so little energy left over in their radical pair, who cared? But photosynthesis knew how to do it. The second thing is this thing is so fast that this pathway is turned off. This pathway, of course, could exist, but it's not competitive with the speed at which charge separation takes place. So this had big implications for how to build a photosynthetic system artificially. So I just fixed their diagram. By fixing their diagram, I just cut out a few of the things. Most of the light comes up here. Electron transfer takes place. It goes to the triplet state, and it returns to the ground state in the system by giving off heat, basically, in the system. All right. But back to the special pair now. I read this, and I became excited, because I had to return to this argument about what was going on in the photosynthetic reaction centers. And at the very last sentence down here, they make the statement that they're returning to the fact that it's just an environmental factor that's involved in the study of photosynthesis, of making the unusual EPR properties of the system. Now, what they did that was more advanced than what Thayer and company did was they invoked theory. And they invoked molecular orbital type theory. But I had been following molecular orbital theory, and they had been making advances in the indoor studies. And these advances in the indoor studies, they would produce a new indoor spectrum of bacterial chlorophyll in vivo and in vitro. And they were different. Anybody in this audience would look at them and they say, well, they're dramatically different. And the interpretations were dramatically different on each one. But the theory was always perfect. For any system that they came up with, you got exactly perfect agreement. So I concluded from this that I could not trust theory in this particular area. Okay? So I thought, well, let's see if we can't do something about it. But before this happened, another event occurred, and I thought this would settle the issue. Dyson-Hofer and Mickle got the structure for the photosynthetic reaction center. And then I just got this out of their Nobel lecture. And you see in there the special pair. And you see that they overlap strongly, and it's quite reasonable that an unpaired electron would be shared between these two molecules. So I thought this would end it, but no, it did not end it. Babcock and O'Malley were still arguing for their model for this system. And maybe they didn't do it so much in print, but when you go to a meeting, boy, this was really something else. And you talk about scary. I think they would put Jack to shame, but maybe I don't know. All right, so there's a way to get around this. Instead of using any sophisticated theory, why don't we just use symmetry? So the idea is the following. Because we have triplets in this system, let's grow single crystals in our laboratory and repeat the experiment that Les and Jack did many years ago, but on a single crystal. Here's a single crystal. There's 3 nanoliters of volume in this crystal. Okay, this is 1 millimeter by 3/10 of a millimeter, and it's a hundredth of a millimeter thick. 3 nanoliters. In fact, what we would do for this, we would, if we wanted to see we had good crystals, if you could not see an EPR signal in this system, you did not have a good crystal. There are 2 things that are happening here. You no longer have the random order. So instead of being lines spread out smoothly over 400 Gauss, they're just piled up into a few intense lines, just like the cation would be. And then the other thing that you have going is this intense, incredibly intense polarization as predicted by Jack. So this little crystal is easy to look at, even though you can barely see it with the naked eye. And I'm sure many of you in the audience, without your glasses, you couldn't see it at all. So what happens here is, in this particular orientation, there are 4 lines. There are 2 weak lines here and 2 lines in the center. And what you do is you rotate your crystal in the EPR field about, in this case, about three different axes of the crystal. Actually, only 2 axes theoretically are necessary, but for reasons that help data analysis, we did all 3 crystal axes. And you can easily fit this to the Peg powder pattern that has been mentioned earlier. It's a very trivial calculation. And so what you do is you find out where the X, Y, and Z axis is for whatever molecule you're looking at. And so when you go and look at the X-ray structure, you can take the two paths of the special pair that was found by Dyson-Hoffer, and you'd find the average geometry of those two, and lo and behold, the triplet axes that we found, which we could match up by the crystals, were almost perfectly aligned along the average of the two systems. And even though this is not a perfect alignment, there's a huge difference if you put the triplet on this molecule versus putting it on that molecule. So this completed my aspect of the thing, and with this I no longer cared what Babcock and O'Malley said, and I think O'Malley continued, but I sort of ignored it. So let me just review here. The work of Jack was exceptionally important to me because he provided the first independent evidence that supported the special pair. In this particular case, what happens is because you have two molecules, you can get the electrons further apart in two molecules than you can in a single molecule. This is the dipole-dipole interaction, so the splitting goes down and the spectrum narrows, and so that's what Jack was talking about there. He launched this field of this unusual polarization, and this gave me the ability to look at the special pair proof based on symmetry. No calculations, just trivial looking at symmetry. And I should point out that even today, this is an extremely important aspect of solar energy research that people are doing. The population of this triplet state, as I mentioned earlier, shows that it has to be efficient, and that if you have this efficiency, you should see only the triplet state populated in the middle level of the triplet state. So this has been used as a criterion in artificial photosynthesis, whether you've really done it right or not. Because this means that the charge separation state is above the triplet state, and you're saving most of the energy at this point in the system. There's another criterion that goes along here. If the electrons don't get too far apart, they stay close together, this won't happen. If they get too far apart, it won't happen. It has to be just the right distance for this to happen. So this has played an extremely important aspect of artificial photosynthesis. And I just presented a few of the things that this had an impact on me. I'm still using this thing today. And from my experience, he was always a gentleman. So I don't know this other side of Jack that has been mentioned. Thank you.
Thanks very much.